Welcome to physics class. In this video, I'll be talking about linear expansivity. Suppose you have a material, let's say this material is present as length L centimeter, right? And the temperature, the temperature of the surroundings of this material is taken to be theta 1, right? It's going to be theta 1 at length L centimeter. So let's say there is an increase in the temperature of the surroundings of this material, and it increases from theta 1 to theta 2, right? So if there is an increase in the temperature of the material, what do you think is going to happen to this material? Yes, of course, this material is going to increase, is going to have a fractional increase, that is a little increase in its length. There will be an increase in the length of this material, right? Let me just put it like this. There's going to be an increase in the length of the material. So what happens here is that this material is present at a particular length at a certain temperature theta 1. It has its original length at a certain temperature theta 1. And when the temperature increases to theta 2, what happens is that the material, there is an increase, a fractional increase, that is a little increase in the length of the material. So in this case, the little increase in the length of the material is known as the linear expansivity. So in this case, I'm going to have my L2 here, right? The second length, that is the linear length in centimeter. So, and this is the first length in centimeter. So what happens is that we are going to note two changes in this case. The first change is there is temperature changes, right? There is change in temperature change, and also there is the original length of the material, that is there is length change. There is length change in this case also, right? So in this case now, the change in temperature I'm going to represent as what? As delta, as this is change, right? Delta theta, which means theta 2 minus theta 1, right? And the change in length I'm going to represent as what? As delta L, which means L2 minus L1, right? So in this case, if a certain material present at a particular temperature, if there is an increase in the temperature of the certain material, there will be an increase in the length of what? Of the material. So that increase is known as linear expansion or linear expansivity. So let me just give you a short definition for this linear expansivity. You can say linear expansivity is defined as the fractional increase in length of the substances when there is an increase or rise in temperature. What I mean is that if whenever there is an increase or rise in the temperature of a material, there will be a fractional increase in the length of the material. Such increase in length of the material is known as linear expansivity, right? And linear expansivity depends on three factors. The first one is what? Is the change in length, that is the L2 minus L1 divided by the change in temperature, which is delta theta, and also the original length. It depends on change in length, change in temperature, and also the what? The original length. The original length of the material. So in this case, I'm going to have my what? My L1, then multiply what? Multiply by theta 2 minus theta 1. So I can simplify this expression to delta L, which is change in length, divided by my L1, right? Multiply by what? Delta theta. Right? That's just it. So now in this case now, my delta L represents increase. It represents increase in length. Or you simply say change in length. That's L2 minus L1, right? So then my delta theta represents increase. That is, let me just say rise in temperature. Rise in temperature of the substance. Then after that, I'm having my L1. My L1 is known as, it's taken to be the original length of the material. Right? Then L2 is taken to be the, let me just say, final length final length after expansion, right? Final length of the material after expansion, that is after there is an increase in length, in temperature rather. So there is going to be an increase in what? In the expansion of the material. Then another thing that we have is I think we have theta, right? So theta 1 is known as the initial temperature of the material, right? Initial temperature of the material. Then we have theta 2, which is taken to be the final temperature of the material. Final temperature of the material. What you guys need to note here is that we have alpha, right? This alpha represents the linear expansivity. You can call it linear expansivity, that is the change in length of a material when there is an increase or rise in temperature. You can call it linear expansivity, or you can see it in another form as I think that's coefficient, coefficient of linear expansivity or linear expansion. Coefficient of linear expansion, and it is known as alpha, right? Alpha. That's just it. The first case I'm having here. This question says steel bars, each of length 3 meter at 29 degree, are to be used for constructing a rail line. So what you need to note here is that the initial length of the steel bar L1 is taken to be what? It's taken to be 3 meter. Then our temperature, which is theta 1, the first temperature, that's what? 29 degrees C. Right? Then after that, are to be used for constructing a rail line. If the linear expansivity, our linear expansivity is alpha of the steel is taken to be 1.0 times 10 raised to power minus 5, then Kelvin inverse. Right? Then after that, we are asked to calculate the safety gap that must be between successive bars. If the highest temperature expected is 41, that is our theta 2 is equal 41 degrees C. And we are asked to calculate the safety gap. Safety gap means the differences between what? Between the length of the bar 1, of the steel bar 1 and steel bar 2. Right? And that is represented as what? As delta L. So we are asked to calculate what? For change in length, which is delta L. So in this case, you can just recall alpha equals to delta L divided by what? L1 into bracket theta 2, right? Minus theta 1. So in this case, I can further simplify the formula as what? As I can have it, by the time I make my delta L sort of formula, I'm going to have the formula for the formula to be delta L equal alpha, then multiply by L1, right, into bracket theta 2 minus theta 1. Right? Then this is my L1. So after that now, I'm going to have it what? Delta L equal my alpha, which is 1.0 times 10 raised to power minus 5, multiplied by L1, which is 3, then into bracket change in temperature, which is theta 2 minus theta 1, and that's 41 minus 29, right? So in this case, I'm going to have it to be delta L equal, that's this is actually, this multiplied by this will give me 3.0 times 10 raised to power minus 5, then multiply by 41 minus 29, that should give me 12, right? I'm having it to be 12. Then after that, I'm going to have this to be multiplied by this will be delta L equals to this multiplied by 12. Then I should be having it to delta L, which is equals to 3.6 multiplied by 10 raised to power minus 4 meter. And that's the answer. So the change in length is 3.6 times 10 raised to power what? Minus 4 meter. Check the second question I'm having here. The question says a metal rod of length 50 centimeter, right? The first length, that is the original length of the metal, is equal 50 centimeter, right? Then it's heated from 40 degrees C to 80 degrees C. That means our initial temperature is theta 1, which is 40 degree, right? And also our theta 2 is equal 80 degrees C, right? Then, so the question says that if the linear expansivity, that is our alpha, if the linear expansivity of the material is alpha, that is, if our linear expansivity is alpha, right? Then calculate the increase in length of the rod. So we are now asked to calculate the increase in length of the rod. So increase in length of the rod is taken to be what? To be delta L, that is change in length, right? So this is change in length, which is the increase in the length of the rod. Then after that, we have our alpha here. Then we have our delta theta. right, to be equal theta 2 minus what? Theta 1. So let's go. If you recall from the formula of linear expansivity, we know that alpha equals to delta L, right, divided by rather L1 multiplied by what? Change in temperature, right? So this simply means that my alpha is alpha, right, equal delta L. I'm going to make it the sort of formula so that I'm going to have my delta L equals to alpha L1 delta theta. Then I'm going to have my delta L to be equal alpha. My L1 is equal to what? 50. In this case, I will have to convert to what? To meter. That will be 50 times, that's alpha times 50 times 10 raised by what? Minus 2, right? Then multiply by my change in theta, which is into bracket 80 minus 40. Right? So this simply means I'm going to have it to be delta L equals to, let me just say 0.5 alpha, because this is 50, right? Multiply by this, that 50 times 10 to the power minus 2 is what? 0.5. Multiply by alpha, that's 50 alpha. Then multiply, right? Multiply by 80 minus 40, that's actually 40, right? Multiply by 40. Then I'm going to have to be change in length equals to 0.5 multiplied by 40, that should give me something like 20 alpha. It shows that the change in length, which I'm asked to calculate in terms of alpha, equals to 20 alpha, because I'm asked to calculate the increase in length or increase length of the rod. So the increase in length of the rod is equal to what? 20 alpha, and that's the answer. So if you find this video helpful, please do well to subscribe to my channel, and I'm going to solve a lot of problems under linear expansivity, and I will drop the link to the video in the description box below. Thanks for watching.